Good morning, ladies and gentlemen. May I have your attention, please? Thank you. And so we've got our last day. We're going to add one more thing with improper integrals, and then we're gearing up for our Unit 4 test, which covers all kinds of things involving integrals. First, though, let's go ahead and see if we can't handle when one of our limits is infinite, right? That signals that we have an improper integral, and we can use our tool of limits to get around that fact and allow us to investigate using the fundamental theorem of calculus. And so what we'll do is we'll consider what's going on with our lower limit there. Our lower limit is approaching infinity, right? It's approaching infinity. And so what we're going to do is we'll rewrite this as the limit as my lower limit a approaches negative infinity, and then we can replace that lower limit of negative infinity with a. We know how to evaluate an integral from a to 0, right, using our fundamental theorem of calculus evaluation part. If we can find an antiderivative for my integrand function, in this case 1 over quantity x minus 2 cubed, then we can simply evaluate at the upper, evaluate the lower, and subtract the 2. Then we'll go ahead and evaluate my limit, if possible, and see whether or not the value of this improper integral exists, or if it diverges. So here we go. What's an antiderivative for 1 over x minus 2 quantity cubed? Well, this looks like straight up power rule, doesn't it? We've got a quantity to the third on bottom is the same as quantity to the negative 3 on top, so we can add 1 to the exponent and divide by the new exponent. So long as we have the derivative of the quantity. Do we have the derivative of my base of this power function? Yeah, that's just 1, right? 1 dx. And so we're ready to go, and we'll go ahead and apply our power rule. Keep in mind that we must keep our limit expression throughout until we do the evaluation, just like when we evaluated limits back in AB. All right, so we've got the limit as a goes to negative infinity of, and we'll find our antiderivative function. Our antiderivative function is going to be add 1 to the exponent, so I get x minus 2 to the negative 2, and then divide by the new exponent would be divide by a negative 2, and then evaluate from a to 0. Which means, go Gadron, we have the limit as a goes to negative infinity of, I'm going to write this a little bit nicer. What could we say? Negative 1 over two x minus 2 squared. Is that better? Is that equivalent? From a to 0? All right, time for the eval. So we'll do the limit as a goes to infinity, I'm sorry, negative infinity rather, of, and let's do upper limit all the way through. So with upper limit all the way through, I get negative 1 over 2 times, if I put 0 in for x, then I get negative 2 quantity squared is positive 4, so it looks like negative 1/8, minus, and then we'll do lower limit all the way through. Minus a negative is plus a positive, 1 over 2, a minus 2 squared. And consider the limit as a goes to infinity. And so we know that this first term is just a constant. The limit of a constant is the constant itself. And so that first term gives me a negative 1/8. Plus, let's consider what happens to the value of this fraction as a goes to negative infinity. As a goes to negative infinity minus another 2 is just more negative infinity. Squared is more negative infinity. And if I have an infinite quantity on bottom, whether positive or negative, and a fixed constant on top, in this case 1, what's the overall value of the fraction approaching? 0. And so this is going to 0, leaving me with the negative 1/8 in front, which means that because this is a finite value, even though it's negative, that's a finite value, the improper interval converges and is equal to negative 1/8. So raise your hand if you had that. Did anybody get the negative 1/8? What does this negative 1/8 value signal about the integrated function? What does this represent? Danny?
It converges.
It converges, yes. This improper integral converges, right? In terms of the integrand function, which has a vertical asymptote at x equals positive 2, which is outside of our, outside of our concern. This is just the, what, 1, 2, 3, cubic, so it means that this portion is going to be below there, right? So let's look at that. What if we had our original 1 over x minus 2? It. And quantity cubed. Oh, no, no. That was actually pretty good. What am I trying to show you here? I'm trying to show you that our function is beneath the x-axis on the interval -infinity to 0. Therefore, right, the value of the integral is going to be negative, right, because we're beneath the x-axis. That's what I'm after geometrically. Cool. What questions do you guys have about number 1? 2? All right, so what's going on here? Well, this time my upper limit is infinite, right? This time my upper limit is infinite. However, this function, the 4th root of x, does exist for all positive inputs, and because my limits on my integral are 1 to infinity, that's all positive, right, x values on the interval. Therefore, I don't have any domain concerns for my interval. So I'm ready to go with the limit expression. Let's rewrite this bad boy as the limit. A limit as my upper limit, I'll call it b, goes to infinity of 1 to b, and I've got the 4th root of x on the bottom. Can I find an antiderivative for 1 over the 4th root of x? Certainly. I'll again use the power rule. Well, the current exponent on my power function is -1/4. Yes? Adding 1 to the exponent produces the antiderivative of x to the -1/4 plus 4/4 is positive 3/4. Divided by the new exponent is dividing by 3/4 is the same as multiplying by 4/3. So I'm going to jump right to 4 over 3. No, sorry. I'm going to do 4/3 x to the 3/4. And leave it probably as a rational exponent. Is that cool? And we'll go from 1 to b. So one more with my limit. We'll now evaluate my antiderivative function at the upper all the way through minus the lower all the way through in accordance with the fundamental theorem of calculus evaluation part. So here we go. I get 4/3 b to the 3/4 minus 4/3, 1 to the 3/4 is 1, it's just 4/3. And consider the value of this limit. So as b goes to infinity, again, this constant is going to stay put at 4/3. But what happens to this first term as b goes to infinity? Well, as b goes to infinity, b to the 3/4 is going to become infinite, times 4/3 is still infinite, and so this is approaching infinity. Remember, infinity, right, is not a particular number, right, a specific value. That's not finite. Therefore, this improper integral does not converge. In fact, it diverges because this value is infinite. Therefore, this diverges. We can't find this value, cuckoo. Considering the original graph, we could have seen that, right? The 4th root of x, the 4th root of x is going to continue to accumulate area as you go farther and farther to the right. So this diverges. Awesome. What questions do you guys have about number 2? Then I need to know who found that. Who already found that diverged? Did you find that on your own? That's good news. All right, so we have to be on the lookout for that on our test as well. And then lastly, as the upper limit approaches infinity, what happens to this? Oh, goodness. Well, firstly, I want to check my domain concerns. If I consider that denominator in factored form, I just want to make sure we don't have any x value concerns on my interval of integration. If I factor that bottom, I get x times x minus 1. Is that right? dx, and so it looks like I've got issues at x equals 0. I've got issues at x equals 1. Are those in my interval of integration? No, so we're okay, right? That's what we're going to look at today when we have problems in my interval of integration. However, I'm stuck on finding an antiderivative for this one, right? Can I do natural log for this one? No. Inverse tangent, because I see that x squared? No. What am I going to have to do as a technique to consider integrating this one by hand? Sophia? Absolutely. We'll have to do a partial fraction decomposition by rewriting that denominator as a product of non-repeating linear factors. I can go ahead and figure out what sum or difference of individual simpler fractions produces that original 3 over x squared minus x and try again. So first we need to rewrite the limit as b approaches infinity of the integral from 2 to b of my original, and I'll put it in fully factored form, and then we'll go ahead and do our aside. What do you mean our aside? We know that this original fraction, 3 over x times quantity x minus 1, can be represented by the sum or difference of individual simpler fractions, a over x plus b over x minus 1. And if I were to create a common denominator here, it looks like a times x minus 1 plus b times x must simplify to give me the 3. So what would be a convenient x value to choose, Riley? If I let x equal 0, then the b term would drop out, and I'd get 0 minus 1 is negative 1a equals 3, telling me that a must equal negative 3. Yes? Another convenient x value, Vivian?
0.
Oh, already did.
Oh, 0. 1.
Good, thanks. So if I let x equal 1, then the a term will drop out, and I get 1 times b equals 3, so b must equal 3. Yay! Which means that I can close this little foray into my algebraic calculation and rewrite my original integrand function now as a plus b, right? That a over x is negative 3 over x. Oh. Do I dare do this? Better just go with the go again, right? So I'll rewrite this whole shman as the integral from 2 to b of, rewritten, I get negative 3 over x plus 3 over x minus 1 with respect to x. I want to pause here and just do a partial fraction decomposition check. Raise your hand if you got the rewritten integrand in parentheses. Who got this far? Yes, that's good news. Okay, so you'll have to do that for sure on your test. It may be part of an improper integral or not, right? But you'll certainly have to deal with partial fraction decomposition. That was a main new topic for BC. All right, so what are we going to do here? Antiderivative function. I'll keep my limit expression as b goes to infinity, and we'll rewrite this as negative 3 ln of absolute value of x plus 3 ln of absolute value of x minus 1, close bars, and evaluate it from 2 to b. Oh gosh. So let's see what happens when I put b into my expression all the way through. When I put b into my expression all the way through, we run into what we did last class, where I've got this negative 3 ln of b is positive because it's positive infinity, so I'll just say 3 ln of b plus 3 ln of b minus 1. And my lower limit all the way through, minus a negative, can I just do plus 3 ln 2 minus 3 ln 1? Oh boy, I tried, Tyler. All right, so what's the problem here? I know where Duloc is. Pick me. Pick me. I know where Duloc is. I can take you to the castle. Right here.
Oh.
as b goes to infinity, donkey? As b goes to infinity, ln of an infinite quantity is infinite. So this is infinite, this is also infinite, and that would signal that the improper integral diverges, except for one problem. This would be really infinity minus infinity, which we all know is, dun dun dun, our indeterminate difference. So instead, we'll condense this using our properties of logarithms into the log of a quotient, right? So this is really a single log. I'm just going to go to the, I'm going to say something. I'm going to see it out. I'm going to hang tight right here. Really, this is 3 Really, this is 3 ln of b minus 1 over b plus 3 ln 2. And I'm going to let that ln 1 just go to 0 right now and be done with it. Yes? Okay. So now I consider this quotient. Well, as b goes to infinity, I get infinity minus 1 is still infinite over infinite is infinity over infinity, which again is indeterminate. And yet, right, I've got an inkling here that this indeterminate, right, form, infinity over infinity, I could either apply L'Hopital's rule after doing the function interchange theorem and say the limit of ln of blah is the same as ln of limit of blah, right? Or I could use that algebraic technique by dividing every term in the top and bottom of this fraction by the largest power of b that appears. We did that algebraically last class, and that was pretty sweet. You guys have this written down? Because I can't handle this page anymore. So I'm going to just start fresh here and get some space. So I got the limit as b goes to infinity of 3 ln of, and we're multiplying everything by 1 over b. And it was b minus 1 over b. And this was minus ln 2 or plus 3 ln 2. Great. All right. So everybody look, this is our technique. Right? We're multiplying everything by 1 over b to the largest power of b that appears in the fraction. What does that do for us? Well, look. Look at this. We get ln of 1 over b times b is 1 minus 1 times 1 over b is 1 over b over b times 1 over b is 1. And how in the world is that helpful? Well, look. As b goes to infinity, what happens to my input for this natural log? Well, this fraction goes to 0. So I get 1 over 1 is 1. And what's the natural log of 1? 0. Thank you, goodness. We've reached the end. I saw some of you had negative 3 ln 1 half. Is that right? Well, negative 3 ln 1 half is the same as 3 ln 2. So that's fine too. All right, so raise your hand if you got that equivalent. So good. Not all of you got to the end here. Many of you. That's awesome. So that's quite a problem. That's why I made it number 3 and not number 1. I didn't want you to get too discouraged too soon. What questions do you guys have about your Bellwork?
Do we have to include that on the test?
You could do L'Hopital's rule, but then I'd be looking for the little h thing. You know what I'm saying?
Yeah.
What do you mean, like L'Hopital's rule? Where was L'Hopital's rule appropriate? Only after you got the quotient, infinity over infinity. See what I'm saying? Only when you got to the infinity over infinity would L'Hopital's rule be appropriate. However, to apply L'Hopital's rule, technically we're supposed to then rewrite this yet again with the ln of the limit of. See what I'm saying? Using the function interchange theorem back to AB. So I think it's easier to do it this way, personally. But, all right, let's pause the recording and take care of our OTL, number 8. Okay, ladies and gentlemen. So last class we investigated improper integrals, right? And we saw that an integral was improper if one of the limits were infinite, or both, right, of the limits were infinite. Today we're going to investigate the second qualifications. If an infinite discontinuity occurs at an endpoint, either the a or the b on my original definite integral, an infinite discontinuity we call synonymous with what feature graphically? Yeah, a vertical asymptote, right? So if there's a vertical asymptote at one of the endpoints, right, then we've got an improper integral. And then lastly, we could have an infinite discontinuity somewhere in between a and b, somewhere on my interval of integration, and that'll be my final our final look. So 2 things to add, and then you're going to have a review time second half. So let's go ahead and again inspect graphically. Oh, we need to break up for the last one is the trickiest one, so I just wanted to include this yet again. If f is continuous on negative infinity to infinity, recall that, and we saw this in our assignment last class, you could break up, right? You could break up this integral at any convenient constant in between negative infinity or infinity in accordance with the property of definite integrals. And so our first step here, we could rewrite this as the integral from negative infinity to any constant value, call it c, of f of x with respect to x, and then plus continuing on, carry on from c to infinity, f of x dx. This then generated 2 improper integrals that you can now replace my infinite limit with a limit as a goes to infinity or limit as b goes to infinity and carry on. So I just wanted to include this one more time because we'll need it for today's discussion. How do we do? Cool? All right. So let's go ahead and remind ourselves that if the limit, right, if the limit of that expression is finite, if it exists, then the improper integral is said to converge and takes on the value of that limit. If that limit fails to exist, that is, it's infinite or it does not exist, then that's our indication algebraically that the improper integral diverges, right? Okay, so let's go ahead and consider the area beneath the curve in the first quadrant of this function y equals 1 over root x. Again, we're going to inspect with the calculator, and then we'll evaluate algebraically, analytically without the calculator, and see if we can make a connection between the two. So let's investigate the original, please. Everybody on your grapher, let's enter our original integrand function, y equals the square root of x, and consider the interval from 0 to 1. So what would be a good window here? 1 over square root of x. And let's go ahead and take a look. Negative 0.25. And I'm going to go maybe 1.25. And we'll go negative 0.25. And I'm going to go 3 and see how that looks. So what are we talking about? Well, we're talking about from 0 to 1, and I've got this area up here where it looks like the function continues to approach infinity as x gets closer and closer to 0, but from the right-hand side. So I don't like that window. I'm going to go and change it now more to like 7 for my y max. Okay, there we go. That's a better picture. So what's up? What are we trying to do, right, graphically? Graphically, we're trying to see if we can find the area in between my function and the x-axis in between 0 and 1. But look, my function continues to grow, right, in y value magnitude as x gets closer and closer to 0, right? And so if I continue raising my y max on my window, what will we see? Well, we'll continue to see that function values rise, right, and yet never get to the y-axis. How come? Right, what feature exists at x equals 0? A vertical asymptote. So this is a situation where we have an infinite discontinuity at one of my limits of integration. That signifies an improper integral. And yet, again, our tool will be a limit. And so we're going to rewrite this improper integral then, right, using limits and see if we can't evaluate the improper integral, right, algebraically and exactly, and see if this is a finite area even though that function continues to grow. We saw the rate at which my function values got towards the x-axis determined last class whether or not we had convergence or divergence. In other words, we continue adding on an infinite amount of area, but yet if it was growing slowly enough, then we could get the overall value of that definite integral, versus if, right, we continue adding on more and more area, but it wasn't shrinking quickly enough, then we did not approach a finite value, and the improper integral was said to diverge. We added on too much area to approach a single particular value. All right, so I want this picture. And I want to go ahead and use calculus to do this. And so in general, the area beneath the function f of x on a to b is given by my integral from a to b of f of x with respect to x. In this case, though, we've got my endpoint of my interval, a, is 0, right? And that is an infinite discontinuity on my function. And so I've got 0 to 1 of, was it 1 over root x? 1 over root x dx, and x equals 0 is not defined in the domain of this function, right? I can't divide, right? I can't divide by 0. 0 is not in the domain of this function, and yet we saw graphically, if we let x approach 0 from the right-hand side, right, we could still try and find this area. So our tool is going to be a limit again. It's just my limits aren't infinity, they're just regular x values, but I have an infinite discontinuity at one or both. So let's go ahead and do this. Ready? This will be the limit as a approaches what? Well, we're letting a, my lower limit, approach what? 0 from the right-hand side. If we were approaching 0 from the left-hand side, it would not exist for sure because my function is not even over here. So we're letting a approach 0 from the right-hand side of the integral of a to 1 of 1 over root x with respect to x. We know how to evaluate the definite integral from a to 1 of a function. We'll find an antiderivative. An antiderivative for my integrand function, 1 over root x, evaluate the upper, evaluate the lower, and subtract in accordance with my fundamental theorem of calculus. It's just that my integrand function, 1 over root x, is a power function. X to the negative 1/2, add 1 to the exponent is x to the positive 1/2, dividing by the new exponent is divided by 1/2 is times by 2. So isn't this the limit of 2 root x evaluated from a to 1? And consider the limit then as a approaches 0 from the right. Is that what you guys are getting for antiderivative? Awesome. Well, that seems pretty easy. Actually, all things considered, I mean, we're dealing with a potentially infinite quantity, and yet I think this is going to be easy to evaluate. I'll plug in my upper limit all the way through, and I get 2 root 1. 2 square root of 1 is just 1 times 2 is 2. Minus my lower limit all the way through is 2 root a. Is that right? Can I evaluate this limit as a approaches 0 from the right? Certainly. Limit of a constant is the constant itself. The key here is that we were letting a approach 0 from the right, and that would be allowed. If we were just letting a approach 0, we automatically must consider the left-hand and right-hand limits, and the left-hand limit of this would be undefined. If x is approaching 0 from the left-hand side, this is not going to exist because a would be a negative value. Can I have the square root of a negative? No. So the key was this little inside the limit, right? My limit of integration, I had an infinite discontinuity at an endpoint of my interval, and that was key here. So we needed to do the one-sided. All right, so what happens to a as a goes to 0 to the right? Then this expression goes to 0. And what do we get? We get 2. Hey, is the value of the improper integral finite? Yes, it's finite. And even though, right, that goes on forever and ever and ever, we can still get the exact area. The area of this shaded region is forever and ever and ever up, still sums to 2. That's pretty cool. Love math. Love math. And if I can get every color up there, then I'll feel more comfortable on our explanations of PDF. Wow! What question do you guys have about the first one? Oh, well, we're only 2 cases to consider. So let's go ahead and consider this new integrand function then. The integral from 0 to 3 of 1 over x minus 1 to the 2/3. So let's go ahead and take a look at this picture, again, inspect it graphically, and then we'll go ahead and use our calculus techniques to see if we can evaluate analytically or if it diverges. So let's go with 1 over and quantity x minus 1 to the 2/3. As I consider the domain of this original function, right, first symbolically, what x value are you concerned about before I even hit graph? Right, what x value am I be concerned about? Courtney? for
Oh, 1, never mind.
1. You guys see if x were 1, then 1 minus 1 makes a 0 quantity on the bottom raised to any, right? Any non-zero quantity is 0. I can't have 0 on the bottom of a fraction. So I'm thinking that I'm going to have problems at 1. Why do I care about this? And then the Bellwork, I didn't care about it? Well, because 1 is smack dab in the middle of my limits of integration versus in the Bellwork, x equals 2, my problem value for that one rational function was way over here on the right, and I was talking about the left-hand quadrants. And so we're concerned because my x value of concern for the domain is right smack dab in the middle of my limits of integration. That's bad news bears. All right, let's go ahead and hit graph and see if we can't get a good picture. I'm going 0 to 3, so I'll go that to maybe 3.25. And I won't do 7, I'm going to do 5. I don't know if this is good yet. We're going to take a look. So Courtney's right. Look at that. Look at that. Right at x equals 1, my function values on either side shoot off towards positive infinity. Right? You guys see that? And so what's going on here? Well, what feature exists at x equals 1? A vertical.
Oh my.
Vertical asymptote. I know. We could have said infinite discontinuity, but that would have, right? That would have given away our chance to say asymptote in class. So we went with vertical asymptote instead of infinite discontinuity. I'm right here with you, Tyler. And so definitely, I want to go back to that 7 now that I went and painstakingly changed it because that was better to begin with. Maybe we'll even go 10. So here it is. Here it is. Stretch it out, baby. Look at that. Okay, so what are we trying to do? Well, we're trying to, right, algebraically find the graphical area in between. I'm going to grab it over here. Right, in between x equals 0 and x equals 3. We're trying to find that area. It's just if we continue to zoom out, right, my function values get taller and taller and taller. The region goes on forever. And yet we may be able to find its area because of the rate of growth there, right? Somehow, right, it's getting closer and closer to that vertical asymptote in such a manner that the value of the improper interval converges, then we can find that area and it is finite. So let's go ahead and set up our integral expression and see if we can find it analytically. The difference here is that my problem x value is right in the middle. So what do we have to do? We've got to break it up, right? We've got to break it up. And so that's what we did with our kind of our warm-up reminder. We're going to rewrite this first as the limit. No, I won't do the limit. First, I'll just rewrite the original, and I'll go from 0 to where? 0 to 1, we're going to break it up at dx over x minus 1 to the 2/3, plus, continuing on, 1 to 3. Cool. Now we get to our one-sided limits. And so we're going to break this up into 2 separate limits. And now we're going to, 2 separate integrals. And now we're going to use our limit, our one-handed limit tool algebraically to evaluate this. And so do we have problems with 0? No problems with 0, right? We have problems with 1. So we're going to do the limit as b goes to 1 from the, which hand side? From the left-hand side of the integral 0 to b of dx over x minus 1 quantity to the 2/3 plus second integral now is the limit, but this time we're going to let a go to 1 from the right-hand side of the limit from a to 3 of my integrated function. Are you good so far with the breakup? Okay. Now let's go ahead and evaluate each of those definite integrals and see if we can evaluate the limit expression after the fact. So here we go. The first one, I still have my limit as b goes to 1 from the left. Antiderivative function for this, again, is power rule. I have the derivative of the base is just 1 dx, so I can go right to my add 1 to the exponent, 2/3, right? On the bottom is the same as negative 2/3 current exponent. Negative 2/3 current plus 1 will be plus 3/3, will be plus positive 1/3. Divide by the new exponent, divide by 1/3, the same as times by 3. So I get, in both cases, 3 x to the, x minus 1 to the 1/3. Is that what you guys are getting? Good. From 0 to b plus the limit as a goes to 1 from the right-hand side of 3x minus 1 to the 1/3 of 0, no, a to 3. Right there. Right there. Okay. We're so close. Feel it. So this is the limit as b goes to 1 from the left of 3. And I'm going to leave the 3 out front and do b minus 1 to the 1/3 minus 0 minus 1 to the 1/3 plus the limit as a goes to 1 to the right of 3. 3 minus 1 is 2 to the 1/3 minus a minus 1 to the 1/3. Ah. All right. Can we do this? I sure hope so. As b goes to negative to 1 from the left, what happens to this? B goes to negative 1 from the left. That's like 0.99 minus 1, right? Is slightly negative, but I'm raising to the 1/3 power, so I don't have issues with that, right? I can do the odd. I can do the odd index devaluation if I'm negative, but this is approaching 0 anyhow, so I'm getting 0 here. Are you guys getting 0? Negative 1 to the 1/3 is negative 1, minus a negative 1 is plus a positive 1, so I'm getting 3 for this whole left-hand side. We get 3 for this. You guys get 3? Yeah! Let's do the right-hand side. 2 to the 1/3 is 2 to the 1/3. Cube root of 2, right? As a goes to 1 from the right, this is 1 minus 1 is 0. To the 1/3 is 0, slightly positive is still 0. So I get cube root of 3. So I'm getting 3 plus, cube root of 2 rather. I'm getting 3 plus cube root of 2. Since the value of the improper integral is finite, the limit converges and we can find that area, and that area equals 3 plus cube root of 2. How bomb is that? I had my concerns when I did the first thing. Riley?
Don't you need the 3 times cube root of 2?
Yes, right here, 3. Absolutely right. I forgot about that for you right there. You're right. Thank you, thank you. So 3 plus, I can get another color in here. There's that 3. Yeah, thank you, that was my mistake. So 3 plus 3 cube root of 2. I had my concerns when we looked at the graph originally, when I had just had the y max of like 3, because it looked far away from the vertical asymptote, didn't it? It looked like there's going to be too much area summed up there for it to exist and be finite, and yet it ends up existing. It's more, right? It's more than our previous values of integrals. We got like negative 1/8 in an earlier one. Here we got definitely larger than that, but that's pretty cool. Awesome. What questions you have about this one? Then we've got a final case to consider. Consider the value of the integral from 1 to 2 of 3 over x minus 2. Okay, so which concern do we have here? Well, in this case, what x value might we be concerned with in terms of domain of my integrated function? Kobe? 2. Is 2 in the middle of my limits of integration? No, thank goodness. That took a long time to break it up like that and do 2 separate limits. It's on an endpoint, so we'll only have to do 1 limit, right? So let's go ahead and inspect the graph, and then we'll see if this value exists or not. So for my y equals this time, we want 3 over x minus 2. And we want from 1 to 2, and so for my window, I'm going to go negative 0.25 still, 3.25 still, I think. And my y values, I'm going to go back towards 5. Let's see what that does for us. So in between 1 and 2 would be right in here. And I'm not seeing anything, so that's bad. So that's not so good. It is 1 to 2, right? Okay. Nope. Did I anything? 1 and 2 is right here, right? Oh, I'm down here. That's why. Thank you. We want this to be maybe negative. There we go. Thank you, thank you.
Oh, there she is.
Ah! We want it between 1 and 2. Thank you. All right, that's the other side of the bass asymptote. Negative 15. What are you doing? I'm trying to find a good window. Ah, you do too much. Get off my case. You're doing too much. They say it East. You're doing too much. All right. So what are we trying to find geometrically? That's what they say.
How do you know?
Sorry, roll. All right. Does that area exist? I don't know. Let's see. I'm skeptical. But I was skeptical last time. You guys see? See what we're talking about? Going forever? Okay. So what are we going to do? We're going to set up a limit. All right. We're going to set up a limit to see if we can evaluate this improper integral. So again, this is improper because one of my limits is an infinite discontinuity. So it looks like the 2 here is causing problems. So let's do the limit as b goes to 2 from the left-hand side of the integral of 1 to b of 3 over x minus 2 with respect to x. That in turn equals the limit as b goes to 2 from the left of, can we find an antiderivative for that? I hope so.
Oh, yeah.
3 ln absolute value x minus 2. Those bars evaluated from 1 to b. Okay. All right. And that in turn is the limit as b goes to 2 from the left of 3 ln of absolute value of b minus 2. This time I'm leaving the 3 in. So I think that's going to go away. Minus 3 ln of absolute value 1 minus 2 is negative 1. And good thing I have the bars, right? Because ln of negative 1 is undefined, does not exist, but ln of absolute value of negative 1 is perfectly all right. Absolute value of negative 1 is 1, ln of 1 is 0, so this term is 0. Let's focus in here. As b goes to 2 from the left, right, that's values like what? 1.99. Minus 2 is approaching 0, but is what sign? Negative, and that's okay, because the absolute value of negative is positive, so we're still okay. But what's it approaching? 0, right? And the natural log of a quantity approaching 0, right, is infinite. It's negative infinity, right? It's approaching. So because the value of this limit is infinite, the improper integral diverges, and that area, right, is infinite. We can't find it. So the improper integral diverges. So since the limit is infinite, the improper integral diverges. you feeling today? You okay? Let's close it up. Let's close it up. So we saw 3 different ways that an integral could be improper. Please be ready to share those. What type of limit must be used when either the upper or lower limit of integration is an infinite discontinuity? And so that's when the endpoint of my limits of integration is an infinite discontinuity. So what type of limit would we have to use then to handle that? All right, so what's one criterion to be improper? So what's one criterion to be improper integral? Grace?
Have an infinite discontinuity at an endpoint.
Good. So if we have an infinite discontinuity at an endpoint, at an endpoint of my interval of integration, then we've got improper integral. Good. That's one. What's another one? All right, what's another one? Brendan?
One or both limits are infinite.
One or both limits are infinite. And our final one, the bear of a one, right? Danny?
Infinite discontinuity. Infinite discontinuity on it.
Yeah, if we have infinite discontinuity somewhere in the middle of my interval, then that's bad news. Potentially. Somewhere on my interval of integration.
Sounds
Great.
good.
So if the infinite discontinuity is at an endpoint of the interval, what type of limit must we use in the eval? Right? What type of limit do we have to use on the eval? Sophia? Absolutely. We had to use a one-handed limit. We had to use a one-sided limit. One-handed or one-sided. Awesome, you guys. So what's up? Well, we got our Unit 4 stamp check, test next class. And while last time we had our maximal cylinder investigation, our extreme values, and then our critical value discussion, this time we just had red marks 1 through 9. So I got 9, including today's. Right? Check back and see if any of those are missing, but I think that we were good to go for 8 days this unit. So go ahead and check back and find those. And then lastly, your OTL. Did I get this on the printout yet? I did? Yep. Hey, great news. So most of these are odd, but you'll notice there's a couple of evens there, like the 3, 4, 5, 6, right? There's 2 evens there, and then number 40 is an even, otherwise they're all odd, okay? The rest of the time then is yours to work, but I do ask that you get your stamp check taken care of first, because I'm going to come around and check in with you and get that on Infinite Campus, so you'll have everything represented going into your test. I'll stop the recording and save it, and take care of our Moodle upload.